Thank you for being part of part 2. We asked you to work the practice problem. We worked a problem that was similar to this. We've asked to find a value and an eigenvector for a share described by kx equals 4 and ky equals 1. In class, work at it, and whatever you can work, if you can't solve it, we'll go over this in class. If not, we will move on to our next point. So as you can see, you have a sheep, and then you shear it, and you take all the what? All the wool off. So we would like to make our applications at this time in reference to circuits. And so we're having an RLC circuit, as you can see, our voltage source with our switch. We have our resistor. We have our inductor, and we have our capacitor. And we have our current flowing through this circuit when the switch is closed. And so the voltage at the source is going to equal to the voltage across all of these elements. And because they're in series, we just add them up. If they're in parallel, we do the inverse. Okay, so we have the voltage for the resistor, the voltage across the inductor, the voltage across the capacitor. What are they equal to? The voltage across the resistor is equal to IR. The voltage across the inductor is L times di dt. And the voltage across the capacitor is 1 over C, the integral of I dt. So what we want to do is solve for I dt. So we would like to take everything and move it to the other side of the equation so that we can be left with L di dt. So that means we have V of S minus IR minus 1 over C, the integral of I dt. Now we're going to divide by L, both sides of the equation, to cancel out the L here. So it's 1 over L, still with our voltage source minus the voltage across our resistor and across our capacitor. We're calling this equation 1. Then we're going to have equation 2, which is we would want to now take since we're taking the derivative of the current, now we're going to be taking the derivative of the voltage of just the capacitor. And so, since that's the integral, and this is, we're taking the derivative of it, the dt's will cancel here, the derivative of an integral will cancel out, and so all we're going to have is 1 over C times I. So this is what we're calling equation 2. So we're going to be using equation 1 and equation 2 to come up with our matrix. Okay, this is equation 1, which we've discussed already. This is equation 2. And so now we combine the two together. We have di dt and dv dt equals 1 equals I. So our vector here is VC. Okay, so what we're doing here is we have I times R minus I times R over L. Then we have here for our voltage, we just have 1 over L. Okay, minus 1 over L. Then and we have also plus our voltage source, and this is going to be a vector by itself, our voltage source, and that's 1 over L. Then we have, for our second equation, looking at dv over dt is equal to 1 over C times I, and there is the other value is 0 for VC here. Plus we have no value for Vs in this equation, so that's also set to 0. So you can look at this as we have our I and our V. Okay? So now we would like to come up with, how do we make this a matrix? How do we put this together? So we're going to be using this matrix here as our main matrix. It is not symmetrical, but it is a square matrix, A, and then this is going to be I and V of C. This is going to be our eigenvalues, our eigenvectors, sorry. These are the vectors that we're going to be using. And our voltage here, our voltage source, we will ignore at this point. So now that we have this equation, di dt over dv of the capacitor dt is equal to a minus r over L minus 1 over L and 1C and 0. This is for I and the voltage of the capacitor. Plus we have, as we mentioned, your voltage source here of 1 over L and 0. So what we want you to do is take the equations like we've been using so far. I explained to you the theory. I walked through you with the equation to be able to come up with our A, and I would like for you to come up with our find the eigenvalues for the circuit described with these parameters. Now, how does R affect this equations, but how does it affect the circuit? And since R is only our real component, and we also have our L and our C, which are both imaginary components, how do they affect our circuit? So you solve this, and we'll go over this in class. If you can't solve it, we'll have you, you can solve it ahead of time. Okay, so what happens when we have a step voltage input? Okay, when we have, for our equation, what you solved, you should have gotten lambda is equal to a minus 1.67 times 10 to the 6, and you should have got lambda 2 equal to a minus 2 times 10 to the 6 power. So what actually happens? Okay, when we have real negative eigenvalues, this means that the damping becomes stable. Okay, so we see it becoming stable, and it's a stable behavior. Okay, why is that? Okay, we have this equation. We're looking at 1 minus e to the minus omega t as lambda equals a minus omega t. Now this is all talking about a negative eigenvalue. The system damps out. It goes to the infinity. As t goes to infinity, okay, as we keep going higher and higher, as time goes toward infinity, what happens? The system goes to 1. Okay, so as this value gets larger and larger, it gets smaller and smaller, and we're subtracting less out until finally. So if you subtracting out at the very beginning, you're subtracting out what? 0 here. 1 minus 1, e to the 0, gives you 0, and it just keeps going. Okay? So now what happens when we change that? Okay? When we take out our resistor and we have a complex, an imaginary number. Okay? Remember I had mentioned to you that L and C are both imaginary components. R is the only real component. Now, as this real component is removed from the circuit, what we have is, as lambda is equal to plus or minus I omega. This is a pure imaginary eigenvalue. It means the system is only oscillating with no damping. Okay, let's look at that for a second. Let's see if we can see this. Okay, so if we have the real part we would like to get of 1 minus plus or minus I omega t. As you can see here, we plug in here for omega t, our minus our cosine omega t, and our sine omega t, our I sine. So since we're only looking at the real part, the I part drops out, the sine drops out, and we just have 1 minus the cosine of omega t, which oscillates between 0 and 1. So when cosine is equal to, cosine starts at what? 1. 1 minus 1 equals what? 0. Then as the cosine changes, it'll eventually hit 1. And then it'll hit negative 1. And then when it's negative 1, then 1 plus 1 equals 2. So it's just going to isolate between 0 and 2. That's because we have no resistor, nothing to dampen it. Okay, so the next thing we would like to know, okay, how can we control and dampen? Okay, so if we have a resistor in now with our two imaginary components, so now we have a complex number. So our lambda is complex with a real part, a negative real part. Remember, we're talking about a negative value, plus or minus the imaginary part. So this is a complex number. And so what we find here is as lambda is equal to the real, the minus, a real part, plus or minus omega. Omega is the imaginary part. We have complex eigenvalues, mean negative real part. So if we have a negative real part, which we talked about before, it signifies damping. And the imaginary part, which we have here, which is e to the plus or minus I omega t, gives us isolation of the current. So as it oscillates, it eventually dampens out. Okay, dampens out to 1. You can see here, it's go to 0, 2, and it'll eventually damp out. So what is damping this out? Let's look at the equation. Okay, if we take this equation, we break it off into two parts. We have the imaginary part, which we have here, which we can write in the sine and cosine, and we have the real part. And if we just look at the real part, we take out the I, which takes out the sine wave, we have left 1 minus e to the minus lambda, or omega, or lambda, okay, times the cosine of t. And so when cosine is, okay, so as t gets greater and greater, it'll isolate, as we mentioned in the beginning, it'll isolate from 0 to 2. And as it oscillates, then we have this damper here that will dampen it out. So as e goes to infinity, it's going to take this to 0, and then it's going to take this to 1. So our value will damp out at 1. And then whatever the number that's in front, the magnitude that's in front, then that'll be the value, because this is 1 and the magnitude can change. Okay, So we'd like for you to also find the characteristic vibration frequency of the following system. We have two masses here. One is double the size of the other, and we have springs here, okay? And they're going to vibrate. So we want to find out what the characteristic vibration frequency. When we talk about the frequency and the vibration, we're going to be looking at the rotation. We're going to be looking about the diagonalization formula, okay? We talked already about how we can, what did we do? Okay, we can rotate around a vector. We also talked about that we can rotate around an axis, okay, and that's when we use sines and cosines. And also we're using another one that's called C. Okay, C can diagonalize, can make our matrix symmetrical. And so what we want to do is we're going to show you an example of why we need to worry about getting diagonals and why we need to worry about the rotation. Okay, so we can see this is moving, it's rotating. This one here is rotating. Okay, this one is bending, and this one is rotating and bending. So the question is, how do we come up with equations that will represent this? And that's what we've been doing. And so there's going to be another equation that we're going to look at where it calls the inertia tensor, describes the system rotational tendencies. Okay, we just looked at the tendencies of how they will rotate. Based on this, we're going to be able to look at our diagonal. And as you can see here, we can multiply a number times our vector. This is our vector here, our omega, and this is going to be our I, our matrix. So now, we can always find an orthogonal set of axes, okay, the x, y, and the z, that we have only the diagonal matrix. That's it. And that makes life much more simpler for us. And so, but this is only true if we can find an I such that a C times our original matrix, that it can transform our original matrix into a diagonal. These C's, our C inverse and our C, will be able to transform this to what we call our diagonal. And so we would like for you to solve a problem using that. As you can see here, this is symmetrical. Okay? These are symmetrical. Find the principal axis and principal moments of inertia for a thin right triangular plait. If the inertia tensor through the plate centroid is, this is what the centroid is. So we have here our C, we have here our H, we have here our Y, our Z, and our X component. So it says find the principal axis and the principal moment of inertia for the right triangle plate. Now, we just showed you, and all we have to do is be able to convert this over into a diagonal. Okay. This is already symmetrical. Remember the other one, we had to have it, it has to be what? Symmetrical, such that the inverse times it can equal, times the matrix can equal a diagonal. That's what we just showed you a second ago. As you can see here, we started here, and notice it's C inverse times the I, the original what? Matrix that we have, times the C, and it's going to give us our diagonal. Okay? So, if you can work that out, and when we come to class, whatever you worked out, that'll be wonderful, and we'll help you walk you through some of these problems that you are working. Well, thank you again for being part of our study. And this is part 2, and this is it for today. Enjoy your day. Thank you. Have a nice day.